All right. Today we're going to go into chapter 6, where we learned how to use entropy. This is lecture 15. It will be aimed at establishing the TDS equation. You'll hear a lot about PDV and TDS equations. With the TDS equations, we will then introduce the use of TS diagram, temperature entropy diagrams, which is the equivalent of using PV diagrams, but for entropy. And then we'll show a few ways by which you can derive entropy. They're particularly easy ways in the case of incompressible substances, and a not so easy way in the case of ideal gases. Of course, just like the other properties, most of the time you have to look entropy up in the thermodynamic tables. Now, let's start with the PDV-TDS equations. So we're going to start from a system that's pure, simple, compressible, and we're going to limit ourselves to these transformations that are internally reversible. So to remind you, the transformation that's internally reversible is when between 1 and 2. When you find the path, it doesn't have to be the path that you're really going to take, but if you can find a path that is reversible, that's irreversible. So we saw before that the change in entropy in such a path could be defined as the integral between 1 and 2 of the change in heat across the boundaries of the system divided by the temperature in this hypothetically, well, by definition, has to be a reversible situation. So if we look at this equation, which is an integral equation, that means that the differential equation has to be essentially the integrand here. So that means that delta Q over T in a reversible system is this entropy change ds. Notice once again the use of the differentials. Delta Q is not an exact differential, but delta Q over T becomes one because entropy is an equation of state. So that is an exact differential. I could write S2 minus S1 to be integral between 1 and 2 of ds. That d would be a Roman d, just like this. Okay. So now that we had this, we can take our first principle again, where we had du, the exact differential of the internal energy, is this differential of the heat in a reversible system minus the work in a reversible system. Well, the work in the reversible system, we have seen this a long time ago, is PDV, so we can substitute PDV there. This dq, take this dq, put the t on the other side, and you have dq is TDS. Substitute these two things into that equation, and you have that the change in internal energy is the temperature times the change in entropy minus the pressure times the change in volume. That's one of your two TDS equations. The second one concerns the use of the TDS equation in the context of an enthalpy. So we just derived this one here, the same hypothesis as we had before. And now let's look at the enthalpy. So H is U plus PV. That means that DH is DU plus P of dPV, which you work out, DU plus PdV plus VdP. Now regroup this. DU plus PdV is DH minus VdP. Bring that over there. So DU, get this DU from what we had on the previous graph. That's CDS minus VdP. Plus VdP, so these two cancel out, is dH minus VdP. Regroup that dH on one side, and then on the other side you have TDS plus VdP. So now you have these two TDS equations, which I will summarize here. du is TDS minus PDV, dH is TDS plus VdP. Notice these are inverted. These equations can be done like I have them here as extensives, or we can use them as intensive if we normalize per unit mass, the lowercase u, lowercase s, lowercase v, lowercase h, lowercase s, and lowercase v here as well. Or we can do it per mole, u bar, s bar, v bar, h bar, s bar, v bar. All right. So what use are my TDS equations? Well, they show you that very much like we use the PV diagrams to represent work, we can actually use the TS diagrams to represent heat. PV diagrams are work, TS diagrams are heat, and of course, one can make HS diagrams, which is sometimes done. It's actually relatively equivalent to TS diagrams. So let's take a look at these favorite TS diagrams. I repeat, just like we use PV diagrams, we can use TS diagrams. So in a TS diagram, T1S1, T2S2, you will have a process that follows a particular path. So just like we had in PV diagrams, the path matters. In the TS diagram, the path also matters. So you have the endpoints, T2S2, T1S1, which are equations of states. So this is the characteristic of state just alongside all the others: specific volume, pressure, temperature, internal energy, enthalpy. Entropy is one of them. That means that when you have your vapor domes and all the properties we went through in chapter 3, you have to identify where you are. So in the PV diagram, we had the vapor dome here, we had the critical point, we had the liquid, we had the gas, you had the isotherm, look like this. In a TV diagram, we had that, just the same way. Well, in a TS diagram, we have exactly the same thing again. We have here a critical point. We have here the saturated fluid, the saturated gas. The isotherm, of course, is a horizontal in a TS diagram, but the isobar, P is constant. Oh, it's not. The isobar is now looks like the isotherm in the vapor dome and then goes up here in the TS diagram. Same thing. So let's take a look at what we can do with the TS diagrams. So just like the PV diagram gave you the integral under 1 and 2, the integral of PDV, so the green area, represented the work for thermodynamic process in the past. Now we are going to have the exact same thing in a TS diagram. If we go from 1 to 2 and we integrate, then we will have the area under it is the heat. Well, but you have to be very careful. This only applies to internally reversible systems. It doesn't apply to real systems. There are corrections in real systems, which we will get to in another lecture. So to internal reversible systems, you can write then that the heat derived by that is the integral of TdS. And so this area is the internally reversible heat for the process from 1 and 2. It's not the total heat. So the irreversibilities, the heats that comes out of friction, they don't show up in this diagram. Okay, so let's take a few particular cases. What happens if we are in the vapor dome? Heat and work during the evaporation. So in the vapor dome, you're here, your isotherm is here, and if you look at the integral of PDV during the evaporation process, so when you go from saturated liquid to saturated gas, you have as area here the work that's done by this evaporation process, if you keep the temperature constant. And of course, because you keep the temperature constant, you keep the pressure constant, but the volume increases. That just means boil water in a piston, the piston slowly goes up. And the work is here. Well, in the TS diagram, we have exactly the same case. Like I explained, TS in the vapor dome, of course, is a horizontal because that's an isotherm. An isotherm is a horizontal, and it's also here, the isobar, whereas here the isobar goes up, the isotherm would keep going up, horizontal. Well, the heat in the TdS diagram is that temperature times the entropy in the gas minus the entropy in the fluid. So you can calculate this is work, this is heat, and of course, because this is an isobaric process, you can get exactly the same result. This minus that gives you the difference in internal energy. And in fact, you can work this out because that way, Q over M is U2 minus U1 plus W over M. W, of course, is P dV. So it's P V2 minus V1. And oh, look, that is H2 minus H1. So the heat here is actually the mass times the difference in enthalpy during an evaporation process. Okay. Now this is something that you have to be careful with. Many problems, you're going to be told that the transformation is adiabatic. Adiabatic is not the same thing as isentropic in general. So adiabatic means that the heat is zero, the change in heat is zero. Isentropic means that the change in entropy is zero. So a system has a change in entropy that is zero when the integral for the reversible part of delta Q over T is zero. But there is always this. There is this entropy produced during the cycle. So to be isentropic, you have to have a system that is and adiabatic and fully reversible so that this becomes zero. You have to have two conditions, adiabaticity and reversibility, to have isentropicity. Now let's take a look at our Carnot cycles. And this is why it was hard to explain, for example, the vapor Carnot cycle in the previous lecture using a PV diagram. It's actually very easy to explain using a TS diagram. Because in a Carnot cycle, you have the power part of the cycle is between 1 and 2, is isentropic transformation. So it's a transformation where there's no change in entropy. 2 and 3 is an isothermal transformation. 3 to 4 is an isentropic transformation. And 4 to 1 is an isothermal transformation in a power generation cycle. And amusingly, in a refrigeration cycle, it turns counterclockwise, just like we had with the PV diagram. So as in the TS diagram, as in the PV diagram, power turns clockwise, heat pumps turn anti-clockwise. Now, the area in the table above, well, so the heat is the TDS, right? It's T hot times S23. So the heat that goes in is this area here. The heat that comes out is S41. So the heat that comes out is this area here. And that means that since the heat in minus the heat out is the work, the area within the cycle is the work produced during the cycle. And therefore, the efficiency of the cycle is the area within over the area under the top line. That's here. All right, let's move on to how you obtain these entropy values in a diagram. So we had in the PV diagram, we had a region that was the vapor dome. Then we had isentropes, and we didn't have isentropes. We had isotherms or isobars. Well, so what do these very same areas look like in a TS diagram? So here we have T, here we have S. The vapor dome looks exactly like it did in the PV diagram. It looks like a vapor dome. Here is your saturated liquid, so S sub F is here. Here is your saturated vapor, so S sub G is right here. And as you move through your vapor dome, either at constant temperature, so if you move at, say, constant temperature, you are going to switch your entropy and at the same time, the quality of your vapor. So just like in a PV diagram, we could use either the specific volume or the quality to determine where we were in the vapor dome. We can do exactly the same thing with the entropy of the mixture in the vapor dome. Now, once we go into the supersaturated vapor, then one has to look a little bit at the shape of these curves. So the isotherm, of course, continues being horizontal. The isobar looks like this thing that climbs up. The isocore, constant volume, looks pretty much the same. And the isenthalp, the ones at constant H, comes down like a hyperbola. This diagram will be used very, very often. You have to become familiar with its use because it's as important as a PV diagram. Another one that's used in some areas of thermodynamics, particularly in refrigeration technology, is the HS diagram, which looks a little different, of course. So you want to look at your vapor dome that looks like this. This is your saturated vapor. This is your saturated liquid. Remember that when we talked about liquids and incompressible liquids, the enthalpy didn't vary very much with temperature, with pressure, for example. So because you actually very often use as enthalpy the value that the enthalpy had at the saturated liquid region. Well, so this is actually the same thing. This difference is quite small here. Now, like before, if we have an isobar, it looks like this. And as you go from here to here, well, you can't get to zero here. This is a decrease in your quality of your vapor. So generally speaking, when you apply your second law, it is very helpful to locate your states and processes on your diagram. And you can pick a TS diagram or a PV diagram, the most common ones, but an HS diagram would help just the same. Two commonly used figures having the same having entropy as one of the coordinates at the enthalpy entropy diagram, which is called the Möller diagram, and of course the TS diagram, which we saw before. Example. How do I use a TS diagram? This is something that we will actually see in chapter 8, but we've already touched on it when I explained the Carnot cycle using a steam cycle. Well, so we take superheated vapor. Well, let's say we take saturated vapor right here. We send that to a turbine where it expands. So this is vapor, which we condense partially in the turbine. Then we send it in a cooling water system where we condense it fully, 2.3. We pump it, we increase its pressure, and we boil it here so that you have the same pressure at 4 as you have at 1. But here it's, let's say, cold liquid, and here it's saturated vapor at a higher temperature. If you look at that in a TS diagram, you start at saturated vapor, which is here. You expand it in a turbine. Well, this turbine is supposed to be internally reversible, ideally. So that means that actually happens at a constant entropy. So it's a vertical here. Well, that gets you a point where there is a certain amount of quality to your steam. So there is and gas and liquid present here, which we then condense fully at 0.3. Condensing fully means we're on the saturated liquid region. Then we pump the water. Well, pumping water will heat it up a little bit. So we go from 3 to 4. A pump, if it's an internally reversible pump with no losses at all, will not change the entropy. And then we can heat it up in the boiler all the way up to here. Now we could make that into an ideal Carnot cycle. If we started from condensing from the vapor here, we condense it partially. We then would put it in the cooling water condenser, this instrument, but we would stop when it's here, and then we would pump it straight up. That would be then a Carnot cycle. Because the pump really is in this case, an isentropic machine. It's kind of idealized, but let's just say that's what it is for the moment. Okay. Now I will show you how to use entropy in a variety of systems that are simpler than the full vapor dome. So let's take a look first in the two-phase regime, which is the hard part. So here you have to look it up with the tables. Here you have to use the quality of the steam. So let's go back. If you are in the vapor dome, inside here, you have a certain temperature that maintains the pressure constant. So let's look at our TdS equations. TdS is dH minus VdP. Well, we hold P constant. So TdS is dH. So ds is dH over T. And that means that if you go from here to here, the transformation is simply the same as the transformation between the enthalpy of the gas and the enthalpy of the liquid divided by the temperature. This temperature is constant, of course, because you're in the vapor dome. If you're somewhere in the middle of the vapor dome at a certain amount of quality X, the same equations apply as you had before for internal energy or enthalpy or specific volume. You can just write the same thing. And we did that before, but we didn't show you how that came from the TdS equations. Now, if we are in the incompressible fluid regime, so we have a specific heat that's not different any under constant pressure and constant volume, and it's just equal to C. We also have, in the incompressible regime, the volume that doesn't change. It barely changes. Well, if the volume doesn't change, the TdS is TdU plus PdV, means that TdS is du. Okay, so du is C dt over T, because U is CV dt, the integral of CV dt, so du is CV dt. ds then is CV dt over T. Okay, so that means that S2 minus S1 is the integral of C of T dt over T. If the specific heat is temperature independent, then the difference in entropy is simply that specific heat times a logarithm of the change in temperature. That comes because the C you can put outside of the equation, and the integral of dt over T is the log T final minus T initial. So that is just the equation that you can use here. Now, if we are going to go far into the subcooled fluid, and we are a situation where the internal energy is not pressure dependent anymore, then the internal energy is the internal energy of the saturated fluid. And just in the same way, from this, you can see that the entropy is just the entropy of the saturated fluid. We had a little correction to apply when it was enthalpy, because the pressure was there explicit. Sometimes when the pressure difference is not too large, you ignore this. But when the pressure difference is large, you have to correct it. No such correction appears in either internal energy or entropy. Entropy here behaves like internal energy, which you actually see right here. All right, we move on to the other part of the phase diagram, of the PVT diagram, and the ideal gas. Way out here, just simplifying assumptions for the ideal gas again. So let me remind you that in general, dH was given by Cp dt. Notice that H is not pressure dependent, the ideal gas, and neither is the internal energy, not pressure dependent, only temperature dependent. Then we had the equation of state, and we had here the relation between specific heat under constant pressure and specific heat under constant volume. Well, let's apply these things now to our TdS equations. TdS is du plus PdV. So let me divide the T out of it. ds is du over T plus P over T dV. du over T, you have that here. du over T is Cv of T dt over T. As far as P over T dV, P over T comes from the constituent equation here, equation of state, and you just substitute R dV over V. Okay, now we integrate this between states 1 and 2. S is an equation of state. Note this is an exact differential. So that means that S in state 2, characterized by temperature 2 and specific volume 2, two parameters to characterize your state, minus the entropy at T1 V1 is the integral of this. Well, so it's the integral of Cv dt over T, which is the integral of this term, plus the integral of that term. Well, R is a constant, a gas constant. So the integral is the integral of dV over V, the primitive of which is ln V, so the difference in the integral is ln V2 over V1. And there we are. We have a simplified equation for the internal energy. But notice that whereas the internal energy is a function of temperature only, Not so the entropy. It's also a function of the specific volume. Let me repeat this exact same thing with the enthalpy. So my TdS now is dH minus VdP. H, take it out of here, dH over T, that's Cp. V over T, from the constituent equation, from the equation of state is R, dP over P with a minus sign, that's from here. Integrated, you change in entropy between state 2 and state 1 is your integral of Cp dt over T, which is the temperature independent part, but there is a pressure independent part. There's a pressure dependent part because you have this log of P2 over P1. So careful, unlike U and H, which depend only on temperature, entropy depends on pressure. And you can then extrapolate that to the case where Cp is a constant. Well, I just did this. You can then extrapolate that to the case where Cp and Cv are constants, like 3/2 R, 5/2 R. Then your integral dt over T of Cv, that becomes Cv T2 minus T1. And if you run the exact same algebra through your entropy change, you have Cv ln T2 over T1 plus R ln V2 over V1, or Cp ln T2 over T1 minus R P2 over P1. So same statement again, entropy is a function of both temperature and pressure. Well, which then leads us to a shortcut, and that is we are going to define a reference state for entropy. This is a bit of a complicated view graph, but the reason is that I simply copied what we had in the previous view graph in the top so that you can watch what happens. What we do to create a convenient table for entropy for gases is we define some reference entropy at some reference pressure, and we define it so that it only takes the first term in this equation, which is a temperature-independent term. So we arbitrarily find a reference state so that we can write S naught as not being pressure-dependent. Well, that reference state is in the book, so it's at 0 Kelvin. And so we're going to have here an absolute entropy, because S naught of 0 is 0. That is the Nernst principle. So once we have that, we can express a change in entropy, in absolute entropy, in S naught. That is just Cp of T. But then when we look at the real entropy, we have this correction term for pressure. So let me just, this is naught minus S naught of T1 is this between the reference and T2, the reference and T1. These two integrals sum to be between T1 and T2. So that is convenient. It really doesn't matter where you put your 0, your Tref, it always comes out. And then you have the same here, if it's per S bar, so I wouldn't even have to add that to the equation. But when you look at the real change in entropy, T2, P2, T1, P1, it's the change in entropy with temperature, which are these S naught values, and then you must correct for the changes in pressure. That is a very important term. The same if we do it per mole. So now, in practice, what you do is you find these S naughts for your gases. For air, A22, A22E in English units. For various other gases, you find A23 and A23E. That gives you the S naughts as function of temperatures. You find your S naughts in your tables, and then you must correct to get your real changes in entropy. You must correct for your changes in pressure as a second step to get your entropies. This, if the entropy is a specific heat, is temperature independent, it still holds. The difference in S naughts, we can see that it integrates to the Cp ln T2 over T1, and then you still have to add the correction term for the pressure, which is ln P2 over P1. And that's it. Thank you.